Hello everyone. Let me continue the chemical equilibrium part. See, let me go through characteristics of equilibrium constant. So today's topic I will continue from this, right? Characteristics of equilibrium constant. See, it is a specific constant for an equilibrium process. It is a specific constant for an equilibrium process. Understand? मतलब process to process the constant may different. So for a particular process it is a constant. So that's why it is a specific constant for an equilibrium process. Okay. Next, it is independent of initial concentration. The magnitude of equilibrium constant is independent of initial concentration or initial pressure. Okay. So, all of you please listen carefully. It is independent of initial concentration and initial pressure also. Next, one more important point. It is independent of presence or absence of catalyst. Presence or absence of catalyst. Okay. So it is a specific constant for an equilibrium process. It is independent of initial concentration or initial pressure. It is independent of presence or absence of catalyst. Okay. Then on which factors it depends? Let me go through that point. Okay. So equilibrium constant depends on what factors? Listen. It's my first step. See, it depends on stoichiometry of the process. It depends on stoichiometry of the process. Okay. For example, if an equation is multiplied by a factor n. If an equation is multiplied by a factor n, then equilibrium constant becomes k1 is equal to k1 power n or k is equal to k power n. So when you multiply an equation by a factor n, equilibrium process, यहाँ पे equation मतलब equilibrium equation, right? If an equation is multiplied by a factor n, the equilibrium constant becomes this is k. That means initial equilibrium constant. Now it becomes k power n. If it is multiplied by a factor n, initially equilibrium constant k है तो now the new equilibrium constant becomes k power n. For example, half H2 gas plus half I2 gas gives rise to HI gas. Okay. Here K1 equilibrium constant can be written as concentration of HI by concentration of H2 power 1 by 2 into concentration of I2 power 1 by 2. Okay, concentration of HI divided by concentration of H2 power half into concentration of I2 power half. Okay, again, same reaction if it is multiplied by 2. Okay, let me multiply the same reaction with 2. तो क्या मिलेगा आपको H2 gas then for H2 gas plus I2 gas gives rise to 2HI gas. then K2 is equal to क्या मिलेगा आपको HI whole square, concentration of HI whole square by concentration of H2 into concentration of I2. Therefore K1 is equal to K2, K1 square is equal to K2. Are you getting it? K1 square is equal to K2, or K2 is equal to the root over K1. Right? Oh, sorry. Right. So again, check is a K2 is equal to concentration of H2 by concentration of H2 into I2. So this is K1 and this is K2. So K1 square, by making this one square, you are getting this one. So K1 square is equal to K2. तो K1 is equal to क्या आएगा आपको root K2. K1 is equal to root K2. So like that you can understand the dependence of equilibrium constant on the stoichiometry of the process. Okay, so this is the first factor, that is the stoichiometry of the process. So equilibrium constant depends on stoichiometric coefficients or stoichiometry of the process. Okay, now let me go through the second factor, that is direction of the process. See, the second factor is direction of the process. Okay, so let me go through this point in detail. How direction will influence the process? Listen, when the reaction is get reversed, we have to take the reciprocal of original equilibrium constant. So better to go through an example. That's very easy, right? For example, N2 plus 3H2 gives rise to 2 NH3 gas. Okay, for this equilibrium constant K1 is somehow 49. Let me take like this. K1 is equal to 42. Then for 2 NH3 gas gives rise to N2 gas plus 3H2 gas. K2 is equal to how much? See, what is K1 actually? Concentration of NH3 power 2 by concentration of N2 into concentration of H2 power 3. And what is K2? K2 can be written as concentration of N2 into concentration of H2 power 3 by concentration of NH3 power 2. Therefore, what is the relation? So, K2 is equal to 1 by K1. Understand? K2 is equal to 1 by K1. Okay. Or K1 equal to 1 by K2. So, like that you have to understand. So, K2 is equal to 1 by K1 or 1 by 49. So, just if you take the reverse of that reaction, you just take better to say, just to consider a reciprocal of that original equilibrium constant. So that's it. So it's about the second and important factor, that is direction of the process. Okay. Here, let me go through one more important point. Okay. If you add two equations, you have to take the product of overall equilibrium constant can be taken as product of those individual equilibrium constants. Kaise? Let me see. Listen. N2 plus O2 gives rise to 2NO. Here equilibrium constant is given as K1. Right, this is the step 1. Step 2, 2NO plus O2 gives rise to 2NO2. Here it is K2. Okay. So understand this, N2 plus O2 gives rise to 2NO. All these are in gaseous state. Again 2NO plus O2 gives rise to 2NO2. So overall equation, this is the third equation. I am writing it as N2 gas plus 2O2 gas. gives rise to 2 and more 2. Then overall equilibrium constant K is equal to how much? Now you are adding these equations now. Therefore K is equal to product of these individual equilibrium constants. So K is equal to K1 into K2. When you added equations, you should take product of equilibrium constants of individual steps. Okay. Similarly, if you subtract it, then you should go for a division. Addition of two processes makes the product of equilibrium constants of the individual steps. When you subtract it, you just go division. Okay. See, later I will explain with a suitable example. एक क्वेश्चन जैसा एग्जाम्पल हम एक्सप्लेन कर सकते हैं क्योंकि ऐसा क्वेश्चंस आर गिवन इन नीट पैटर्न. So many previous questions if you check it, then either addition subtraction करके so उसका आंसर निकलता है. ठीक है? Right. So this is about equilibrium constant and its characteristics. The third and important factor is temperature. I'll have to go through this. Temperature. The next factor is the temperature. Yeah, equilibrium constant depends on temperature. Now listen. See, the dependence of equilibrium constant on temperature. The dependence of equilibrium constant on temperature is explained by using Van Hoff's equation. Right, the dependence of equilibrium constant on temperature is explained by using Van Hoff's constant. Okay, what is this Van Hoff's constant? ln K2 by K1 is equal to del H by R into 1 by T1 minus 1 by T2. Or it can be written as log to the base 10 of K2 by K1 is equal to del H by 2.303 into R into 1 by T1 minus 1 by T2. Okay. Now one thing you have to understand, that is del H. Okay. Where del H is equal to heat of the reaction. So in this equation del H is equal to heat of reaction. So K1 is an equilibrium constant. K1 equal to equilibrium constant at T1. K2 is equal to equilibrium constant at T2. K1 is equilibrium constant at T1, K2 is the equilibrium constant at T2. Okay. Now listen, if del H is equal to 0, see del H 0 means it is called a thermoneutral equation. Thermoneutral equation. For such cases, K1 is always equal to K2. Understand? If del H is 0, this whole part becomes 0. So log 1 is 0 na. If del H 0 होगा तो ये whole part 0 हो जाएगा. Then log K2 by K1 is 0. Therefore log 1 is 0. So K2 by K1 is always equal to 1. So K1 equal to K2. Okay. Next, if del H is positive means what? Endothermic reaction. Del H positive means endothermic reaction. तो क्या होगा? As T2 greater than T1, K2 greater than K1. If del H is positive, we call it as endothermic reaction. In such case, as temperature increases, equilibrium constant increases. As T2 greater than T1, K2 greater than K1. Okay. So coming to one more condition. If del H is negative, right? That means it is exothermic reaction. exothermic reaction. In this case, as T2 greater than T1, as the temperature increases, K2 less than K1, equilibrium constant value decreases. Clear? So here you have to write the two important conditions. See, I'm writing here. Otherwise, I will wipe it off and I'll give you. Right. See, for an endothermic reaction, equilibrium constant increases with increase in temperature. Understand? For an endothermic reaction, equilibrium constant increases with increase in temperature. Similarly, for an exothermic reaction, it decreases. वो भी point लिखिएगा. For an exothermic reaction, equilibrium constant decreases with increase in temperature. So understand? So these are the factors which influences equilibrium constant. One is direction of the process, other one is stoichiometry, and the third one is temperature. Okay. Now I'll give you a small question here. Okay. So all of you, please check it. It's a graphical question. Right. So I have go through a graph like this. ln k versus 1 by t graph is given like this. So what is the nature of equilibrium process? मतलब I'm asking it as exothermic. First option exothermic, second option endothermic, third option thermoneutral, and fourth option is none of this. Okay. So if you see ln k versus 1 by t graph is like this, a positive slope, not from horizon, it's a positive slope. So what it indicates, as the temperature increases, equilibrium constant decreases. ln k versus 1 by t as per Van Hoff's equation, as the temperature increases, k value decreases. Therefore, it is an exothermic reaction. Understand? From this particular graph, as temperature increases, equilibrium constant decreases. That's why it is an exothermic reaction. Okay, right. Next, अभी तक आप characteristics of equilibrium constant देखा. Now let me go through applications. Listen carefully. Applications of equilibrium constant. See, I am just writing here K. I am not differentiating to Kc or Kp. You just take दोनों और similar way behave करते हैं. One is in terms of concentration, one is in terms of partial pressure. Both behaves in a similar way. That's why we are taking like this. Okay. Application of equilibrium constant K. Okay. So its first application is it is used to predict extent of reaction. Okay, it is used to predict extent of reaction. Sir, क्या है sir extent? It's very simple. Forward is more extent or backward is more extent. That's we have to find. So it is used to predict extent of reaction. Okay. Now, all of you listen carefully. If K, मतलब equilibrium constant is greater than 10 power 3. If equilibrium constant value K greater than 10 power 3. So, what do you consider here? Forward reaction is in more extent. अब यहाँ पे फॉरवर्ड रिएक्शन इज इन मोर एक्सटेंट, फॉरवर्ड रिएक्शन ज़्यादा होने का चांसेस है. ओके, सो द हाईएस्ट वैल्यू ऑफ K indicates that the process is almost going to completion. So I am writing that point also. The highest value of K represents that the process is almost going to completion. The process is almost going to completion. Okay, so if K is greater than that of 10 power 3, usually forward reaction is in more extent. अगर इससे भी ज़्यादा है तो मतलब highest value of K is always indicates that the reaction is almost going to completion. That's you have to remember. Okay. Now intermediate value of K देखेंगे. Second, intermediate value of K. So listen to this. Intermediate value of K मतलब है if K lies between, the value of K lies between 10 power minus 3 to 10 power 3, both forward and backward reactions, both forward and backward reactions are in comparable extent. In comparable extent. So we can make a comparison. Okay. So slightly forward ज़्यादा है और slightly backward ज़्यादा है, वैसा हम compare कर सकते हैं. ठीक है? कब if it is 10 power minus 3 से 10 power plus 3 तक, right? If the value of K lies between 10 power minus 3 to 10 power 3, then both forward and backward reactions are in comparable extent. Okay. And one more last point. If K less than 10 power minus 3, if the value of equilibrium constant is less than 10 power minus 3, then backward reaction is in more extent. Backward reaction is in more extent, right? So reaction hardly proceeds. Okay, what we can say? Reaction hardly proceeds. Reaction hardly proceeds मतलब in forward direction it's a very difficult to proceed. So reaction hardly proceeds at this condition. So like that you can predict the extent of reaction on the basis of K value. Okay. Okay, right. And one more important aspect here is reaction coefficient. So all of you, and we go through that point also. So the next one, reaction coefficient. Reaction coefficient. So it is represented with a capital Q. Reaction coefficient Q. Okay. So what is reaction coefficient? Listen. Reaction coefficient is always equal to ratio of product of molar concentration of products divided by product of molar concentration of reactants. Right. So Q is considered to be like this. Product of ratio of product of molar concentration of products to the product of molar concentration of reactants. That's taken as a Q. Now sir, what is the relation between Q and K, sir? Formula to almost similar लग रहा है. Yes. See, listen. If Q is equal to K, we can say the process is exactly at equilibrium. If Q is equal to K, the process is exactly equilibrium. That means both forward and backward reactions are in same extent. forward and backward reactions are in same extent, means the same velocity se ja rahe. Next, if Q greater than K, then what happens? Backward reaction is in more extent. Backward reaction is in more extent. Okay. If Q less than K, then what happens? Forward reaction is more extent. Forward reaction is in more extent. Understand? If Q is equal to reaction coefficient is equal to K, we can say it is equilibrium. If Q greater than K, backward reaction is in more extent. If Q less than K, forward reaction is in more extent. So this is a reaction coefficient and in relation with the equilibrium constant. Okay. Next. See, one application we completed. That's what extent of the process के बारे में we can use this equilibrium constant. The second thing, we can predict the molar concentrations of the reactants and products at equilibrium. Okay. See, second application, prediction of molar concentrations of reactants and products at equilibrium. Reactants and products at equilibrium. Okay. Prediction of molar concentration of reactants and products at equilibrium. So we can predict or we can find the values, right? See, first case 1, del m is 0. अब case 1 में क्या ले रहा हूँ? Process का del m 0, मतलब no change in gaseous number of moles. Sum of number of moles of product is equal to sum of number of moles of reactant. In such case, del n is equal to 0. Okay. So, वैसा reaction निकलेगा H2 gas plus I2 gas gives rise to 2HI gas. Okay. Now, initial concentration. आप चाहिए तो A moles, B moles वैसा ले सकता है. I want to make it in a simplest way, so I want to take 1 mole, 0. 1 mole per concentration मतलब you just take it a mole per liter. Okay, this is initial concentration. Right. Next, the final concentration, or sorry, finally equilibrium concentration. If you take equilibrium concentration, ये 2x लेंगे तो ये वाला 1 minus x होगा, ये वाला 1 minus x. मतलब here x is considered to be degree of dissociation. 1 mole से x mole dissociate हो रहा है, तो product क्या होगा? 1 mole gives 2 moles, so x mole gives 2x. So HI concentration 2x and इसका 1 minus x, इसका 1 minus x. मैं यहाँ पे directly concentration ले रहा हूँ. अगर कोई moles लिया गया तो initial moles at equilibrium, then it should be divided by V, क्योंकि concentration means number of moles by volume. मैं already यहाँ पे लिख चुका हूँ concentration, so you should imagine it mole per liter. Already volume is included. Okay. Next, you better to go through total moles at equilibrium. Total moles at equilibrium कितना है? 1 minus x plus 1 minus x plus 2x. तो कितना आएगा? 2 moles आएगा. 1 minus x plus 1 minus x plus 2x. That's 2. Okay. Now for this equation, what is Kc? Equilibrium constant Kc in terms of molar concentration. क्या ले सकते हैं? So concentration of Hi whole square by concentration of H2 into concentration of I2 at equilibrium. Kc can be calculated from equilibrium concentrations. So I think I just write like this: equilibrium. Okay, EQ means equilibrium, right? So 2x whole square by 1 minus x into 1 minus x. Okay. So Kc is equal to 4x square by 1 minus x whole square. So like that you can predict मतलब if you know the Kc value and extent of dissociation you can able to find. So वहाँ से आप reactant का concentration कितना है, product का concentration कितना है, वैसा find out कर सकता है. ठीक है? So this is the case one where del n is equal to 0. Similarly, if you want to find Kp, similarly Kp अगर चाहिए तो ठीक है, Kp is equal to how much, right? So Kp के लिए क्या करना है, पहले पार्शियल प्रेशर ऑफ HI लेना पड़ेगा. तो 2x is the partial pressure. मतलब partial pressure मतलब क्या लेना है, 2x by 2 into total pressure, number of moles by total number of moles, mole fraction into total pressure ना. So partial pressure of HI is equal to 2x by 2 into P. Okay, फिर ऊपर से स्टार्ट कर रहे हो हम. So ये ठीक है. Next, partial pressure of H2 is equal to 1 minus x by 2 into P. Partial pressure of I2 is equal to क्या, 1 minus x by 2 into P. So this is the partial pressure of HI, this is the partial pressure of H2 and this is for I2. Then if you want to find Kp, Kp क्या होता है, Kp is equal to partial pressure square of HI by partial pressure of H2 into partial pressure of I2. तो Kp is equal to ये 2x whole square मतलब 4x square into p square by 2 square मतलब 4 divided by इन दोनों का प्रोडक्ट मतलब 1 minus x by 2, ऐसा लिख सकते हैं 1 minus x by 1 minus x whole square में मल्टीप्लाई करके ले रहा हूँ by 4 into p square. 4 get cancelled. P square get cancelled. So Kp is equal to 4x square minus 1 minus x whole square. Understand? So Kp is equal to 4x square minus divided by 1 minus x whole square. So like that you can predict a Kp and as well as Kc. See, this is the case one where delta n is equal to 0. Okay. So in the similar way, delta n not equal to 0 also ले सकते हैं. Okay. So I am going to case 2. If delta n not equal to 0 and delta n is negative. Okay. Best example for this, N2 gas plus 3H2 gas gives rise to 2 NaH3. Right? 1 mole, 3 mole and 0. Now it is 2 alpha, 3 minus 3 alpha, नहीं है तो 2 minus 2x, 3 minus 3x, 1 minus x. Alpha भी ले सकता है, that's what I meant here. So this is it. Now, bubble, this is initial concentration and it is concentration at equilibrium. Concentration means moles per liter. So total moles. Okay, again यहाँ पे कुछ ये होते हैं. Total concentration अगर कर लेंगे तो अच्छा रहेगा, ठीक है? नहीं है तो इस इक्वेशन में से वहाँ पे del n 0 है ना, तो एट लास्ट वॉल्यूम, अगर वॉल्यूम लिया गया है तो वो भी कैंसिल हो जाएगा, ठीक है? सो दैट इज del n 0 होने से नो वॉल्यूम टर्म और नो प्रेशर टर्म. ओके, ये वॉल्यूम लेके करेंगे. सो प्रीवियस मॉडल में वॉल्यूम नहीं लिए थे हम बिकॉज वहाँ पे फाइनली del n 0 है तो कैंसिल हो जाएगा, इसलिए मैं कॉन्सेंट्रेशन डायरेक्टली यूज करके किया. बट इन दिस केस अगर कॉन्सेंट्रेशन जगह आप इनिशियल मोल्स एंड मोल्स एट इक्विलिब्रियम, इनिशियल मोल्स एंड मोल्स एट इक्विलिब्रियम ऐसा लिया गया तो तब क्या टोटल मोल्स कितना होगा, 1 minus x plus 3 minus 3x plus 2x. Okay, 1 minus 2x. Okay, total moles 1 minus 2x. Therefore, equilibrium concentration अगर चाहिए तो अभी क्या लिखना है, equilibrium concentration 1 minus x by v, okay, for n2, 3 minus 3x by v for h2, 2x by v for NH3. Therefore Kc is equal to क्या आएगा? Kc is equal to इसका होल स्क्वायर मतलब 4x square by v square by 1 minus x by v into 3 minus 3x by v whole cube. Okay. Then ये सालों करने से क्या आ रहा है देखो, तो 4x square by v square by 1 minus x by v into 3 minus 3x by v whole cube. So v square कैंसिल करने से फिर भी और एक v square ले रहे यहाँ पे, तो 4x square into v square by, right, 4x square into v square by 1 minus x into 3 minus 3x whole cube, right? So again I'm writing यहाँ पे shade आ रहा है, light का shade आ रहा है. So Kc is equal to 4x square into v square by 1 minus x into 3 minus 3x whole cube. So this is the Kc. Okay. So Kc can be derived like this. So if you know Kc, from that you can find x value, from that you can find the concentrations of reactants and products at equilibrium. Right? So this is the case 2 where delta n is not equal to 0 and that to negative equal. Now sir Kp value भी बताइएगा, तो Kp के लिए let me try again. Right? So I am going, okay, see in the next class I'll go through some questions based explanation also. Right, until now I used to give theoretical approach. Right, in the next class some critical questions on equilibrium, how you can solve, that will I'll definitely explain. Right, and one more thing, I am not a regular YouTuber. See, this method is quite new for me, so that's why thoda sa voice clarity or something, so many people are telling like that. See, I don't know that technology that much problem. I want to help to the student community. That's why I'm posting some videos, right? So please like, share, and subscribe this channel. Kindly, please, right? Okay. Now, here is 3 things. Case 2. If delta n is not equal to 0 and del n is positive. Okay. For example, PCl5 gives rise to PCl3 plus Cl2. ऐसा एक इक्वेशन देख लीजिएगा where delta n is positive. Next, initial moles. I'll take 1 mole, 0, 0. Right. See, moles at equilibrium. Moles at equilibrium. Here x, 1 minus x. So total moles at equilibrium. Total moles at equilibrium can be written as 1 minus x plus x that equal to 1 plus x. Okay, clear? Right. Concentration at equilibrium. Concentration at equilibrium, if you see, x by v for chlorine, x by v for phosphorus trichloride, 1 minus x by v for phosphorus pentachloride. Okay. So therefore Kc can be written as what? The product of these two, product of molar concentration of products by reactant. So x by v into x by v by 1 minus x by v. So it can be written as Kc is equal to x square into v by 1 minus x. X square into v by 1 minus x. Understand? So this is about Kc if del n is not equal to 0. If del n is positive, you should go through like this. Now sir, go through Kp derivation, right? Okay, again I'll go through again. So Kp कैसे कर सकता है? So first you have to find the partial pressures, right? So partial pressure of Cl2 is equal to x by 1 plus x into total pressure. Partial pressure of PCl3 again x by 1 plus x into P. मतलब as a number of moles equal होगा तो partial pressure भी equal हो जाएगा. Partial pressure of PCl5 is equal to 1 minus x by 1 plus x into P. Right. Therefore, Kp is equal to partial pressure of PCl3 into partial pressure of chlorine by partial pressure of PCl5. So, Kp is equal to x by 1 plus x into P, x by 1 plus x into P by 1 minus x by 1 plus x into P. So 1 plus x, P get cancelled. So final expression I am writing here. So Kp is equal to what you are getting, x square into P by 1 minus x plus 1 plus x. Right? So Kp is equal to x square into P by 1 minus x square. So this is the final expression for Kp. So like that you can predict concentration of reactants and products at equilibrium. You can predict partial pressures of reactants and products like this. Okay. So this is about applications of equilibrium constant. Okay. One more point. Spontaneity of the forward process also we can see. Right? Spontaneity of the forward reaction. What I mean to say, either forward reaction is spontaneous or non-spontaneous, we can understand from this. Forward reaction is spontaneous or non-spontaneous, isn't it? According to thermodynamical studies, okay, listen all of you. According to thermodynamical studies, right, del Z is equal to del Z naught plus 2.303 RT log Q. Also already I already taken a derived equation, right? Del Z is equal to del Z naught plus 2.303 RT log Q. Okay, where Q is the reaction coefficient. Just now only we described it, right? Right. At equilibrium, क्या लिख सकता है, Q is equal to K and del Z is equal to 0. At equilibrium Q is equal to K and del Z is equal to 0. Therefore, del Z naught is equal to minus 2.303 RT log K. Now this is the relation between standard Gibbs free energy change and equilibrium constant. Del Z naught equal to minus 2.303 RT log K. Now one more thing, यहाँ पे temperature standard temperature लेना है, मतलब 298 kelvins. In this expression, temperature is taken as a standard temperature, that is 298 kelvins. Okay. Now listen. If K is equal to 1 and del Z naught is 0, that indicates exact equilibrium. It is exactly in equilibrium. मतलब forward and backward reactions are in same extent. Okay. If K greater than 1 and del Z naught is negative, so forward process is spontaneous. But the forward process is considered to be spontaneous. If K less than 1 and del Z naught will be positive, so forward process is non-spontaneous. Understand? K equal to 1, del Z naught 0. Process is at equilibrium, both forward and backward in same extent. If K greater than 1, del Z naught is negative, so forward process is spontaneous. If K less than 1, del Z naught is positive, then for forward process is non-spontaneous. Okay. So this is about applications of equilibrium constant. Understand all of you? See, or one more class is required to complete the remaining part. Let me go through some important questions. After that, some questions के साथ साथ some important points for the coming IIT JEE and NEET के लिए भी कुछ हम कर सकते हैं. और one last topic is that it's Reactants principle. So I try to complete this topic in one more class, right? Thank you all. So meet again in next class. So please like, share and subscribe this video. Thank you all.